Now in this video lecture we would be talking about Bohr's model of atom. Before this we have already done till Rutherford's model of atom, and we see that it has some significant contribution towards the model of atom, but it has some drawbacks also. Right, let's first revise, or let's just recall what were the drawbacks of Rutherford model. Right, drawbacks of Rutherford model. Right, the first drawback was that it could not explain, it contradicted the stability of atom. Right, it could not explain the stability of atom. Could not explain the stability of atom. Right, because if you remember, it said that electrons are revolving around the nucleus in different orbits, right? And Max Planck theory, or I'm sorry, the Clark theory said that whenever a charged body revolves around in a circular path, right, whenever a charged body is moving or revolving, it will radiate energy, right? So when it will continuously radiate energy, that means it's losing energy. So when it is losing energy, it will keep falling into lower orbits, right, that are closer to the nucleus, and finally it will fall into the nucleus, thereby destroying the nucleus, right? But which is contrary to the fact that the atom is stable. Atom doesn't get destroyed, it is stable. So this theory was wrong, right? That electrons are revolving around the nucleus, right? Because electrons are charged, and charged bodies when revolving will lose energy, and as per that rule it should fall into the nucleus, thereby destroying the nucleus. So this was one of the drawback. And there was one more drawback: it could not explain the line spectra of elements. Right, it could not explain the line spectra of elements. So we'll be talking about line spectra now, right, in this video lecture. Line spectra of elements is when you have say sodium atom, right? When sodium atom will radiate wavelength and you pass it through a spectroscope, right, then that spectroscope will resolve, right, that radiation that is coming from sodium metal into its constituent wavelengths, right, into its constituent radiations of different wavelength, right? That is your line spectra. So what is the reason for the line spectra, right? Then we'll be looking more into detail in next video lecture about the spectra of hydrogen, right? Or it will be called as fine structure, hyper fine structure of line spectrum of hydrogen atom. We'll be doing that in detail in next video lecture. Then there was another point in Rutherford model that it just said that electrons are revolving around the nucleus in various orbits. He said that electrons are revolving at a very high speed, right, in different orbits around the nucleus. So it didn't say much about the energies of those orbits, right, and energies of electrons revolving around the nucleus, right? So no clear picture was given with respect to the electrons revolving around the nucleus in various orbits, and he didn't talk much about the energies of the orbits in which electrons are revolving, right? So no clear picture of electrons revolving around the nucleus, right? Now after this came the Bohr model. Now there was one important contribution of Rutherford model, and the contribution was the discovery of nucleus, right? and protons inside it, right? This discovery of nucleus was due to famous Rutherford scattering experiment, if you remember. So the nucleus, whatever he discovered about the nucleus, that nucleus is at the center, right? And the entire mass of the nucleus is the entire mass of the atom is concentrated in the nucleus, and it is due to the positively charged particles that are inside the nucleus, and it is due to these positively charged particles that the nucleus is your positively charged, right? And these positively charged particles are protons inside the nucleus, right? So this was the contribution due to Rutherford model, right? Now let's talk about what Bohr, right, added to the structure of atom, because Bohr model is nothing but it's the improvement on Rutherford's model, right? Now Bohr model, which is an improvement on Rutherford model of atom, right, uses Planck's quantum theory, right? In order to describe the structure of atom, right, he uses Planck's quantum theory. And here, if you remember, we said that electrons are revolving at a very high speed like this, right, around the nucleus, and it uses the concept of continuous energy, because Maxwell said that when a charged particle is moving at a high speed, right, here electron, it will continuously radiate energy. So here we are talking about continuous emission of radiation like this, right? So when we talk about Planck's quantum theory, as per Planck's quantum theory, the energy is radiated not continuously but in the form of small packets, right? Energy is radiated in the form of small packets like this, and these packets are known as quanta, right? So energy is radiated in the form of quantum, which are small packets of energy, right? This is the concept that is applied to the model of atom by Bohr, right? So Bohr applied Planck's quantum theory to the structure of atom. Bohr applied Planck's quantum theory to the structure of atom, right? And this is Bohr model of atom is improved form of Rutherford model of atom, right? And as per Rutherford model, this was the contribution, right? So the first point as per the Bohr model is that the first point of Bohr model says, it tells us that an atom consists of a massive positively charged nucleus, right? Like this. This is your nucleus, right? And around the nucleus, these electrons are revolving in these energy levels, right? This is a positively charged nucleus which Rutherford already discovered, right? And electrons are revolving around this positively charged nucleus, right, in these energy levels, right? The electrons are moving around the nucleus in certain fixed circular orbits. These are fixed circular orbits. Electrons are revolving around these fixed circular orbits, right? Electrons are revolving around these fixed circular orbits without radiating energy, right? The non-radiating orbits, these are non-radiating orbits. Electrons are moving in these orbits without radiating energy. These circular orbits, fixed circular orbits, are known as stationary states. Stationary orbits or stationary states, we call these, right? So now let's just concentrate on the structure of atom, more on the electrons revolving around these and these fixed circular orbits, right? We'll be talking much about these. Now he said that electrons are revolving in fixed circular orbits, right? And electrons are not radiating energy. Make sure you understand this, that electrons are not radiating energy. Like here earlier Clark said that electron, when a charged particle is moving, right, it will continuously radiate energy, hence will continue to lose energy, right? This was said by Clark. Now Bohr said that electrons will revolve in this fixed circular orbits without radiating energy, right? And these non-radiating orbits, right, these non-radiating orbits are known as stationary states, right? These are known as stationary states. Now these are stationary with respect to energy. Make sure you understand these. We say these as stationary orbits or stationary states with respect to energy, not with respect to electrons, because electrons are not stationary. Electrons are revolving around in these. Electrons are revolving in these fixed circular orbits, which are stationary orbits, right? So electrons are not stationary. These orbits are stationary with respect to the energy, right? These orbits are stationary with respect to the energy, right? So second point was that these energy levels, these stationary states, right, or these fixed circular orbits, each of these fixed circular orbits have definite amount of energy associated with it, right? Each of these circular orbit has a definite amount of energy associated with it, and this energy will keep on increasing as you keep moving away from the nucleus, right? We know this from the structure of atom that we have done in previous classes, that the energy of the outermost orbits is highest, right? This was declared by Bohr, that as you move away from the nucleus, the energy of these stationary orbits will keep on increasing, right? And these energy states are represented by K, right? Not like this, it's the inner one. We will start it from the inside one, K, L, M, N, right? Or we also call these as N is equals to 1, N is equals to 2, N is equals to 3. So stationary orbits or energy orbits are represented by K, L, M, N or 1, 2, 3. N is equals to 1, 2, 3. And if we later will learn that this N is known as principal quantum number, right? For now, just remember that each of the fixed circular orbits, right, is associated with a definite amount of energy. Hence these stationary states, right, are also called as energy levels, since they consist of definite amount of energy, right? These stationary states consist of definite amount of energy, so we call these as energy levels, right? These are energy levels, right? Why we call these as energy levels? Because each of these stationary orbit, right, stationary states consist of definite amount of energy. Since they consist of definite amount of energy, which we say will keep on increasing as we move away from the nucleus, right? So we call these stationary states as energy levels, right? These are also known as energy levels, right? Now the energy, there's a formula to find the energy associated with an energy level is given by a formula. The formula is energy associated with any of these stationary states or energy level is given by En is equals to minus, it's n square z square e to the power of 4, right? It's 2 pi square, the formula is 2 pi square z square e to the power of 4 m upon n square h square, right? It's 2 pi square z square, z is your atomic number, e is the electronic charge, e to the power of 4 it's the electronic charge, m is the mass, right, mass of the electron, then n is your energy level, this n stands for the energy level, then h is your Planck's constant, right, h is your Planck's constant, and remember this energy, the energy of any of these energy state or energy level is negative, right. So if you put the value of pi z, let's calculate this energy for the simple atom hydrogen, right. For hydrogen atom z is equals to 1. If you put the value of E, then mass, then Planck's constant, right, pi, all these are constants, this will come out to be, energy will come out to be minus 1312 upon n square, right, it will come out to be minus 1312 kilojoules per mole, minus 1312 upon n square kilojoules per mole, right. This is the energy of a stationary orbit or the energy of an energy level, right. So as you keep moving away, as the number n will increase, that is you keep moving away from the nucleus, this negative value will keep decreasing, right, that means energy will keep increasing, right. So this formula is important, you may get some numericals on this, right. Now let's talk about similar atoms like hydrogen, like lithium atom, right, or helium atom that has same number of electrons, like hydrogen is 1 electron. Now let's talk about lithium, right, and your helium. For helium first, we have Z is equals to your if you calculate energy for your helium atom, for helium we know that atomic number Z is equals to 2, right, and for lithium we have Z is equals to 3, right. So for simple atoms like hydrogen, right, that have 1 electron in their outermost shell, this is 2 plus, we have for helium we know that for helium Z is equals to 2. So if I put here 2, then this energy would be 4 times the energy of hydrogen atom. This would be 4 times the energy of hydrogen atom. Similarly, if we talk about lithium, for lithium the atomic number is 3, right, atomic number is 3. Therefore, energy of lithium is equals to, if you put 3 here, Z, because all other E, M, H, Planck's constant, N, right, all these will remain same. The only thing that is changing here is atomic number. Because why everything is same, even E is same. Why? Because it's these atoms, lithium, helium are similar to hydrogen atom. They have 1 electron in their outermost shell. That is why we have written plus 2. That means lithium has lost 2 electrons. Here helium has lost 1 electron, and now it has 1 electron like hydrogen atom. So here the energy associated with lithium would be minus 9 times of hydrogen atom, right. This is the energy of simplest atoms like that of hydrogen, right. Now the different energy levels are not equally spaced. These energy levels as you keep moving away from the nucleus, these energy levels are not equally spaced. So write it here. These energy levels are not equally spaced. What that means is that the difference in energy as you move up, as you move away from the nucleus, the difference in energy, right? The difference in energy between energy levels, the energy difference, to be correct, the energy difference between energy levels will not be same, right? That is why we say energy levels are not equally spaced. That is, energy difference will not be same as you move away from the nucleus, right? So here the most important point is that these electrons, right, are moving in the stationary orbits, right? And these stationary orbits are also known as energy levels, right? And the energy of these energy levels will keep on increasing as you move away from the nucleus. And the formula to calculate this energy is this, right? And we have put the value of all the constants. For simple atom hydrogen, it is this, right? Now the energy is negative. We have used the negative value here. Why? What is the reason for using negative value? What we have considered here is that when the electron that is revolving, that is electron associated with the atom, right, when it is at infinity distance from the nucleus, right, when it is not under the attraction of nucleus, when it is away from the nucleus, very much away from the nucleus, its energy is zero, right? Energy let's write it this way. If you look at this formula, right, energy is equal to 0 when n is equals to infinity, right? That means electron is at a far distance, at infinity from the nucleus. So at infinity it has no influence of this nucleus, that is, there is no attraction between the nucleus and the electron, right? But when it is brought closer to the nucleus, as you keep coming closer to the nucleus, the attraction between the electron and the nucleus keep on increasing. And we know that whenever the interaction is attractive, like in chemical bonding, the energy is released, right? Energy is given out, right? So when electron will come close to the nucleus, the attraction between nucleus and electron will increase, thereby releasing energy. When energy is released, then when the energy is released, that means energy will decrease. So when the energy of electrons, when it is close to the nucleus, is less, right, compared to when it is at infinity distance, right? Because we know that if you apply this formula, En is equals to 1312, when n is equals to infinity, this term is 0. So we have taken the energy of electron as 0 because it is at infinite distance from the nucleus. So when it is coming close to the nucleus, the attractive force increases between the electron and the nucleus. So whenever there is attraction, the interaction is attractive, then energy is released. The energy is already 0. So here we are saying when electron is coming close to the nucleus, energy would be released. So energy is decreasing. It's already 0 at infinity, right? So when it is close to the nucleus, it will become negative. That is why we have taken the energy as negative, because when it will come close to the nucleus, due to attractive forces, energy would be released. Since energy is already 0, so when energy would be released, right, it would become negative, because when energy would be released, energy will decrease, right? It's already 0, so when it will decrease, it will become negative. That is why energy is taken as negative, right? Now another important point is that these electrons, right, that are moving in circular orbits, these since these are circular orbits, right? So these circular orbits has, since they are moving in a circular orbit, so every circular path has angular momentum, right? Similarly, these orbits also has angular momentum. So these electrons will not randomly move in any of the orbits. Like Rutherford said that electrons are moving in various orbits around the nucleus. He did not say much about in which orbit or what kind of orbits. So Rutherford said that since these are circular orbits, so every circular orbit has an angular momentum associated with it. So electrons will move only in those orbits that have angular momentum, which is whole number multiple of h upon 2 pi, right? H upon 2 pi. This is what declared by Bohr. Bohr said that electrons will move in only those circular orbits that have angular momentum. Angular momentum is given by mvr is equals to nh upon 2 pi, right? This is the third point now we are discussing. This is the third point. So angular momentum mvr is equals to nh upon 2 pi, where we say n is the whole number multiple 1 2 3 4, right? So angular electrons will move only in those orbits, only in those circular orbits that have angular momentum equal to whole number multiple of h upon 2 pi, which is a constant, where v is your tangential velocity. Since it is moving, electron is moving in circular orbits, so it has tangential velocity. V is tangential velocity, r is radius, right? So nh upon 2 pi, right? So this is again an important point, that electron will move, right, only in those orbits that have, since electron is moving, so it has angular momentum, so it will move only on those orbits, only those orbits are permitted for which angular momentum is integral multiple or whole number multiple of h upon 2 pi, right? This you should remember. Now, since electrons are moving, right, so what about the radius? What about the radius of these orbits? There is a formula that is used to calculate the radius of the orbit, which is n square h square upon 4 pi me square z, right? The radius of the circular orbit is given by n square h square upon 4 pi square me square z, 4 pi square me square z, right? So if you put the values of all the constants, it will come out to be Rn is equals to 0.529 n square, right? Rn is equals to 0.529 n square, right? Angstrom. This is the radius of the orbit, right? 0.529 n square angstrom, right? Now the fourth point is the energy is emitted or absorbed discontinuously in the form of packets. Like I said, the energy of these electrons that are revolving around the nucleus would be emitted or absorbed in the form of packets, of energy known as quanta, right? So electrons that are revolving around the nucleus, we say that the energy is emitted or absorbed discontinuously, right, in the form of packets only during electronic transition between two energy states E1 and E2, right? Let's say these are two energy states. This is E1 and this is E2, right? So when electron will gain energy from E1, then only it will move to E2, right, to the higher orbit. So when electron will gain energy, right, it will move to a higher energy state, right? And when it will at higher energy state, it would be, higher energy state is an unstable state, so it will quickly move back to the lower energy state. So when it will move back to the lower energy state, it will emit radiation of frequency nu, right? Let's say it will emit radiation of frequency nu, right? We will continue.